Hello guys, in today's video we're gonna see the Hahn-Banach theorem for norm spaces or real norm spaces. Let us look at the statement of the proof. Let X be a real norm space and X0 be a proper subspace of X. F0 is an element in the dual space of X0, which is X0 star. Now there exists an element F in the dual space of X such that F restricted to X0 is equals to F0 and the norm of F is equals to the norm of F0. Now before I proceed with the proof, I would give you a general idea of what's gonna happen. So what's gonna happen is that I'm gonna use my previous theorem, the Hahn-Banach theorem for real vector spaces. So let's look at the statement. So in the case of real vector spaces, I had a capital X, a sublinear mapping which was defined on all of X, and X0 was a proper subspace. F0 was given a linear mapping with this condition, and then I showed that F exists with domain being all of X and together with this property holding and this property holding. Take a look at this theorem for a minute before you proceed on to the next one. So the difference between this one and the one we are doing right now is the one here uses P, but we do not have any P in the Hahn-Banach theorem for norm spaces. So what we do is we convert, or we do a bit of trickery and construct a P. And now we have a P defined. Now if you look at this theorem, there is no P. So what I do is I construct a P and then use the Hahn-Banach theorem for real vector spaces. Now let's look at the construction. So now we know that the formula P of X equals to norm of F0, norm of X for every value of X belonging to capital X. So this is important because now my P of X is defined from X to R. See, it defines a semi-norm for X. Now, if I have X belonging to X0, then of course this property holds. So I just take the modulus, then I use Cauchy-Schwarz inequality, and this was by definition construct P by defining it. So this is the way I constructed my P. Now I have a P. So now I have this condition from Hahn-Banach theorem for real vector spaces that this is always less than P of X, which implies that it's equals to norm of F0, norm of X. This is given. I have seen this condition a million times before, that F0 X is less than equal to norm of F0, norm of X0. But now the interesting thing is, by giving this construction, I have defined a P for my norm spaces. Now in the case of real vector spaces, I had this P, and now I just had to show that there exists a F which is defined on all of X together with this property. But as soon as I have this construction, so when I have this construction that there is a real vector space, there is a sublinear mapping with this property holding. Now as soon as I have this construction, immediately I can use Hahn-Banach and say that indeed my F goes from X to R with F of X less than equals to P of X. So if we go to the proof for Hahn-Banach for norm spaces, I can see that immediately once I have this condition, I can use the Hahn-Banach to extend F0 to capital F and together with this property, which is nothing but P of X being greater than or equal to F of X for all value of X belonging to capital X. And now it follows that F is bounded with norm of F less than or equal to norm of F0. Now how come I got this property? I got this property because I know that this, let me write it down again, I know that this is less than or equal to Mx. So the norm of F has to be less than or equal to m. This is what we have seen in the first few videos of the series. Now I see that f is bounded together with this property. But on the other hand, I see when I look at the definition of my f naught, the norm of f naught is equals to the sup norm of f naught x divided by norm of x, which is equal to the sup norm of f of x. Now you might ask, why can I consider f of x here and f naught x here and equate them? The reason is that this x is constricted to x naught in both the cases, and that is why these two things are the same, because as we have seen that if you would look a bit up, then you would see that this construction, as soon as I used Hahn Banach, I had this construction, but f restricted to x naught is equals to f naught. So that is the reason why in this step, f restricted to x naught is equals to f naught. But again, if I have this part, now I need to go from here to here. Why is it this less than? The less than sign is introduced because now my x is not just restricted to x naught, but to all of x. And this is the definition of norm of f. So now we have one direction and here we have the other direction. So indeed, norm of f is equals to norm of f naught. And that's why we have proved the Hahn-Banach theorem for real norm spaces. Let's do a quick recap. What did we do? We started with a real norm space, and x naught was a proper subspace of x, and I had a functional defined on x naught. I had to prove the existence of a functional in x star such that f restricted to x naught is equals to f naught and the norms being equivalent. So the way I did it was I defined p of x to be this quantity using this formula, and once I had a p of x, I converted this formulation into my formulation of real vector spaces with p. And once I had a formulation in terms of the real vector space, I used the Hahn-Banach theorem for real vector spaces to prove that indeed there exists a capital F with this property. And then I showed that not only that, but the norms are also equivalent. So that's the proof for Hahn-Banach theorem for real norm spaces. See you in the next video.